gene for it to show up in that population. Otherwise, it's going to be hidden and masked, and you'll never see it until it finds that pairing again, which is one of the reasons why red hair is actually way more widespread than we even really know, because it remains hidden. If you've got brown hair and brown eyes, you may have a red-haired allele as a recessive gene that you can pass on to offspring, and you may never know, and they may never know that you actually have that red-haired gene in you someplace. So this is where gene flow spreads throughout populations through admixture, right? Genetic drift is the concept of something drifting away from a population. So gene flow are things flowing together, and genetic drift is it drifting away. And so for instance, your book has an example of fish. So if you've got a population of 10 fish, right, in a pond, and 9 of them are gold and 1 of them is red. If a predator comes into this pond and eats one of the goldfish, and you've got 9 fish now, you can stand to lose one of the goldfish because you've got 8 other goldfish. You're going to see that allele, that gold gene of looking like a goldfish, move into the next population. It still exists. But if that predator comes in and the one fish that it eats is the one red fish, that means that that allele has been eaten. It's been taken away. And you won't have that allele in that population anymore. That has drifted away. So randomly, genetic drift has taken that away. Now this has some repercussions for all sorts of things that we'll look at when we look at these, when we look at genetics, in terms of population movements and speciation. So they're very real characteristics, they're very real mechanisms in gene flow and genetic drift in evolution, but they're a little bit bigger picture. They work on populations, and they can be looked at and modeled statistically. Now, deoxyribonucleic acid is the molecular basis for evolution, and its structure, the double helix structure of the DNA molecule, is something that we're going to talk a bit more about next chapter and how it works. But from Mendelian genetics, just the basics of what Gregor Mendel found, people started already understanding and working on what genes can do for us in terms of things like health. We've identified that there are a range of conditions and syndromes that arise from genetics, genetic mutations, recombinations, and already, just even before we decoded the genome, the human genome, we were already able to identify genetic health issues. And this all comes from the structure of the way DNA, deoxyribonucleic acid, is structured. And most of you probably know the names Watson and Crick, who received the Nobel Prize for their work on discovering the double helix structure of DNA. But I've made it my mission to teach everybody about the forgotten member of this group who died before the Nobel Prize was awarded to them. And unfortunately, the Nobel Prize Committee does not award or grant awards to deceased people. So unfortunately, Rosalind Franklin, who was really crucial to understanding the structure of DNA because she worked with microscopic photography, and she actually photographed the first photograph of DNA, which provided the basis for Watson and Crick to unravel the structure of DNA. She was the really crucial member of this team, but she died before the Nobel Prize was awarded, and so she's forgotten about. So I want you all to remember her name, Rosalind Franklin. So we're going to come back and we'll talk more about DNA and how it relates to human evolution in the next chapter. All right.